Okay, today I want to take a minute to remind you about how to do refraction. Remember, on Tuesday, your sub is going to have some refraction problems for you to work on. This is all review from last year, so nothing is new. Very quickly, I want to refresh your memory. Refraction is the bending of light as it passes at an angle. Can't be coming in straight in, as it passes from one material into another of different optical density. Couple notes. One is be careful about optical density. It's got nothing to do with the physical density that we study normally, the mass per unit volume. Optical density really describes how the speed of light changes as it moves into the new material. You recall last year when we shoot light from a laser into water, for example, it slows down and it bends as a process. And that optical density is described by using something called the index of refraction. You remember last year we used the letter N to describe that index of refraction, which in turn describes the optical density of the material. Index of refraction is something you may not have done very much last year, but index refraction is defined as the ratio of the speed of light in vacuum, which is 3 times 10 to the 8, divided by the speed of light through some material x. Couple important things. First of all, it's dimensionless because we're talking about the speed of light in vacuum or the speed of light through materials, so those obviously cancel. It's a unitless quantity, dimensionless quantity. And notice that the speed of light in vacuum is always the maximum number, so this value of index of refraction is always greater than 1 or equal to 1. So for example, obviously the speed of light of the index of refraction in vacuum would be 1. Air, it doesn't slow down significantly, so the index of refraction of air is about 1. Water is when you start to see the speed of light change. It has an index of refraction of 1.33. Therefore, if you do the calculation, if you solve for the velocity of light through water, divide the speed of light through air by the index of refraction, you get about 2.25 times 10 to the 8. So it slows down. It's actually pretty significant. It slows down a good percentage. And this index of refraction number tells you how much it slows down. So the larger the number, the greater the speed reduction. Diamond is the most common high index of refraction material. Diamond has index of refraction of 2.42, and therefore the speed of light reduces significantly. You can do the calculation if you like to. Hours of fun. The other thing I'm going to remind you about is something called Snell's law. Snell's law allows us, I'm not going to do the derivation, but Snell's law allows you to relate the indices of refraction, index of refraction of some material A and material B, and the angle at which the light comes in and then exits. So for example, if we have the, I'm going to try something new here. If I have the material over here, Na, and again, that's not working too well. If I have the material here, Na, sometimes Mr. Horgan, I think, put N1 and N2, and then we have NB. So we're traveling from one material into another material of different optical density. If the Na is greater, if NB is greater than Na, in other words, it's traveling from something that's easy to travel through, like air, into something that has a higher density, like water, you may recall that the light ray will bend towards the normal. And again, the significant thing to remember is that all angles in optics are relative to the normal line. I've drawn the normal line as the green dashed line. This is the boundary. So we're going from air into water, for example. This is the normal line or the perpendicular line. So all of our angles have to be measured relative to that angle between the normal line and the light ray. And likewise, the same thing's true here. Here's our angle. So in this case, when we go from a when we go from a low density into a high density, the light bends towards the normal. When I go from a, when I do the opposite situation and go from a high density into a low density, will actually bend away from the normal. So again, you may recall this from last year doing calculations. The other thing to remember is that you have to make sure your calculator is in degree mode. Okay. The last thing I want to show you is something to do with critical angle, and critical angle only happens when you're going from something with a high density into low. Most of the time when you send the light ray in from high density into low, it does exactly what we normally talk about. So the light ray comes in and it bends away from the normal line. So that's a regular old refraction. There's also a special case that if let me change the color here. If I go from a and you saw this last year, if I come in a very, very large angle, remember, relative to the normal line, then in some instances the light ray will bounce off. And that's because we're beyond what's known as the critical angle. And you can see from this example that the blue ray came in, small angle, refracted. Red light ray came in, reflected, large angle. There's some angle in between there, which is known as the critical angle. And I'll show that in green. There's some angle here where the light ray technically will come out along the boundary. So the blue represents regular old refraction. Red represents beyond the critical angle, where you actually get what we call internal reflection. In that case, the angle of incidence for the red is equal to the angle of reflection for the red. And then you'll have a special case where the light ray comes in along the critical angle and goes out along the boundary. You may recall, if that's the case, you're going to get an error message. Your calculator will actually take the error because they're trying to take the inverse sign of something that's outside of the 90 degree. So give that a try and try the problems for tomorrow. Absolutely.